the last thing we'll cover in this unit is optimization. So real quick, if you were to Google optimization for a definition, you would get the action of making the best or most effective use of a situation or resource. So best or most of something means you're optimizing. So when we apply this to our idea of calculus, when it's something the best or the most is when it's the highest point, the maximum. In some instances, if you're trying to like make the cost of something the best, you're actually looking for the minimum or the lowest cost. So optimization, we're talking about this in calculus, is basically just an applied use of finding an extrema. So optimization is just a fancy word of saying you have a word problem and then you want to find a maximum or a minimum. So let's look at this one. A farmer is creating a rectangular garden using 100 feet of fencing. What is the maximum area she can enclose? All right, well, we want to maximize area. All right, so the area of a rectangle is length times width. But we have no idea, well, we actually do because of like implicit differentiation stuff. But when we're doing these problems, we want to just work with our single variable. And right now there's two variables, there's length and width. So we need to figure out a way to relate these so we only have one variable. The way we're going to do this is we think about the picture. We have the length and the width of our rectangle. The thing we haven't used yet is that we're using 100 feet of fencing, which is going to be what we wrap around the outside of this rectangular garden. And that 100 feet of fencing is going to get broken up into a W part, an L part, another W part, and another L part. So this gives me a relationship between W and L. And I can solve this for either of the variables and then plug it into my area formula. So let's solve it for L. For no specific reason, you do it for either one. And I said divide by 2, 50 minus W. So now I know no matter what, because I'm restricted to this 100 feet of fencing, that 50 minus W has to equal L. So I can replace that in my formula. That gives me 50W minus W squared. All right, so now this is good because now I have a function that only has one variable. And now I want to think about how can I maximize this? Well, to find the maximum of something, that's finding your absolute max. And to find our absolute max, we have to break it up into two parts. So the first thing is find our critical points. Right, to do that, we take the derivative. It's going to be 50 minus 2W. And it never is undefined, so we just have to set it equal to 0. And that is 50 equals 2W, W equals 25. And after we find our critical points, remember absolute maxes can happen at the endpoints as well as the critical points. So the endpoints would be if my width was 0, and the other would be if my width was 50. Because that'd mean I'd have no length or no width. All right, and then 25 is my critical point. If I plug either the 0 or 50 in, I get 0 for my area, because basically it's just a straight line of fence. You're not going to get any area. And if I plug in 25, I'm going to get 625. All right, so my maximum area I can enclose is 625 feet squared. All right, but you can see the process. You just have to create your own formula, but then after that, it's the same stuff we've done with finding absolute maxes and mins. All right, one more. We want to construct a box with a square base that has an area of 36 feet cubed. All right, so we have the square base of a box, and looks something like this. We know the total area is going to be 36 feet cubed. That tells us how much it's going to cost to make the top. So this part, again, you can imagine that part at the back are going to cost $8 per square foot, and these sides are going to cost $6 per square foot. I want to find the dimensions of the box to minimize the cost of producing it. As we think about this box, all right, it's a square base, so this side of these are all going to be the same. And then we have the length, the kind of depth of the box. Let's call it D for how deep the box is. Right. So if you think about what the amount is going to cost. All right, the cost is going to be $6. Oh, sorry, not $6, $8. I'm going to do $8 first. All right, for the end pieces, how much is the end piece? It's s squared, but there's 2 of them there. So that is going to be how much it costs to make the ends of the box. Right. The sides of the box, it's $6. The area of a side is S times D, right, that rectangle. And there's 4 of them. All right, so all in all, I'm going to get 16s squared plus 24 SD. All right, so that is my cost function based on the dimensions, but I have 2 variables right now. I have S and D, so I need to figure out a way to get rid of that. And the way we're going to do that is using the one piece of information we don't have written down anywhere, and that's the 36. All right, so what is the 36? That's the area of the box. The area of the box is the side times the depth, right? There's 3 dimensions make up the area of a box. I want to replace the D here because that's the variable, the easiest one to replace because there's only one of them. So I'm going to solve this for D. 36 over S squared equals D. And now I can take that and plug it in for that D. S doesn't change, but now D is 36 over S squared. A bit of simplifying already here. 24 times 36 over just a single S, because that S and one of those S on the bottom cancels. All right, and that is our cost formula. That's a lot of work to make the cost formula, and now we have to find the minimum. All right, we want to minimize cost, so I'm going to find the minimum of this. So what we do is we find the critical points by taking the derivative. And then setting that equal to 0. All right, there's a few different ways you could go about this one. Maybe here I would just multiply everything by S squared to cancel out that fraction. So turn this into S cubed minus, and then 24 times 36. I haven't figured that out yet. 864. And then add 864 to the other side. And then I have to divide that by 32, which is 27. And take the cube root, and I get S equals 3. All right, so now that I know my one critical point is 3, I also think about the kind of extreme values. So what would be the extreme values here? Let's think about that for a second. I guess technically for the extreme values, we can make them as small as we want or as big as we want. So we made the sides really big. We just have to make this depth really, really small. And if we made the sides really small, we just have to make the depth really big. So I guess for our exchange, we'd have like 0 and like almost infinity, because I could just make this really, really big box that has almost no depth to it at all. All right, but if we plug in 0 into our cost function, we get undefined. We actually can't plug in 0 because of that 0 there. All right, so that doesn't even work, which makes sense because we can't have a box with exactly 0, but a little bit bigger than 0 is still not gonna work. If I plug in infinity, I'm gonna get infinity because of that. So really 3 is the only one I actually need to plug in. So if I actually plug in 3, I'm going to get, let's see, 16 times 9 is 144 plus 864 divided by 3, 288. And 144 plus 288 is 432. And because the extreme values don't really make sense, you could even try to plug in like 1 and 100 or something like that, you'd end up getting bigger numbers. So this is our minimum cost for producing the box. All right, $432 to produce this box. So here's the general strategy for completing these type of problems. Writing them out in words isn't really great because everyone's a little bit different, but there were some similarities between the two examples we did. So first, write the equation for the thing we're trying to optimize. So in the first one, that was the area equation. The second one, that was the cost equation. And use as many variables as you think you need to use. All right, if there's only one variable in that, great, because you just skip a few of these steps. If there is more than one variable, what you're going to do is use the constraints of the problem. So constraints are the restrictions. Whether we're 100 feet of fencing or a box that has an area of 36 feet cubed. All right, so use those constraints to make an equation and find a relationship between the variables that you have. You can plug that in to make sure your equation only has one variable. And then from there, it's finding the critical points. And the way we find critical points is we take the derivative, set it equal to 0, and then test the critical points and to find the extreme values, and then just figure out which one makes sense for your problem. So again, written in words is not super helpful, but the basic idea is you know which thing you're trying to maximize or minimize, whether it's area or cost or something like that. Use other formulas to simplify that equation into one variable, and then just treat it like any of our extreme value problems of finding an absolute max or min. And this slide says basically once you create that one variable equation, it's the exact same as a lot of the other problems we've done of finding an extreme value, right, critical points and endpoints, and then interpret which one's the max or min that you need. All right, and this is the skill that I actually need to practice more of, making that equation, versus the actual calculus is pretty much just one step of taking that derivative and finding critical points. All right, the kind of pre-calc type concept of putting these things together to make the one variable equation is actually the most difficult part of these optimization problems.